Hello everyone, and welcome back to Mitchell's Physics Review. Today we're going to be looking at rotational kinematics. Let's look at our question. A disk 8.1 centimeters in radius rotates at a constant rate of 1,170 revolutions per minute about its central axis. So part A is saying determine its angular speed. So first we can label our givens that r is equal to 8.1 centimeters and the period is 1,170 revolutions per minute. For our equation, we're going to use angular velocity equals 2 pi times the period. First though, since they're asking for radians per second, let's get revolutions per minute into revolutions per second. We do this by dividing 1,170 revolutions per minute by 60 seconds per minute. It equals to 19.5 revolutions per second. Next, now that we have the period, we're going to multiply by 2 pi to get that it's rotating at 122.52 radians per second. Next, we're looking to determine the tangential speed at a point 2.9 centimeters from its center. So, for this problem, we're going to be converting from angular quantities to linear quantities. To do that and to find a speed, we know that v is equal to the angular speed times the radius. The angular speed we just found, which is 122.52 radians per second, times the radius of 2.9 centimeters. But for this problem, we have to convert it into meters, because it's meters per second, not centimeters per second. So we have it 122.52 radians per second times 0.029 meters to get a tangential speed of 3.553 meters per second. Next, we're determining the radial acceleration of a point on the rim in the magnitude, and we need the units to be kilometers per second squared. So let's take a look at how we're going to do that. First of all, it's important to note that radial acceleration can be written with the same formula as centripetal acceleration. Since centripetal acceleration is a linear quantity, we need to use the equation that will convert angular quantities to linear quantities. So we have radial acceleration equals angular velocity squared times r. Now we found our angular velocity already, but how do we find the radius? Well, we're given the radius of the disk and we know the point is at the edge of the disk. The only thing we do from there is convert 8.1 centimeters into kilometers, which is 0.000081 kilometers. Then we do the algebra of squaring and multiplying to get that the radial acceleration is 1.22 kilometers per second squared. Now, if radial acceleration is the same as centripetal acceleration, what way is it going to be going? What direction will it be moving? Well, centripetal means center seeking, so we know that it's going to be accelerating 1.22 kilometers per second squared towards the center of the disk. So, finally, we're going to determine the total distance a point on the rim moves in 1.9 seconds. Now remember, we're moving in a circular path, and when we want to find how much an object moves out of a chunk of a circular path, we're going to be looking for the arc length. The equation for our arc length is arc length equals radius times angular displacement. Then we can plug in the angular velocity times time times r. Finally, we can plug in our angular velocity, we can plug in the given time and the radius, this time in meters, and then we can do the algebra to find that the arc length is equal to 18.86 meters. Now, let's examine this problem conceptually through an angular velocity versus time graph. First of all, our y-intercept should be the initial velocity. In this case, the initial velocity was 0, so our graph should be starting at 0, 0. Next, the slope of this graph is angular velocity, or angular acceleration. Since the angular acceleration is constant in this case, it should be a straight line. Finally, the area of the graph is the angular displacement. So, now that we've analyzed our graph of angular velocity versus time, let's review everything as a whole. This problem, we learned about conversions from angular to linear units, and we learned more about our rotational kinematic equations. Personally, what I struggled with the most was problem A, because I could not figure out the equation. I was struggling with what could be plugged in where and the substitution aspects of it. I think it was easiest when I looked at some of the equations for rotational kinematics and when I looked at the graph to help myself visualize more what I could do to find the angular velocity. I hope you learned a lot this video just like I did. Have a great day.